Great, thank you so much. I'm so excited to be here because I have been saying for years, and you know this, Chris, that the biology is not going to solve all of our problems, and we have to engage with the engineering community. And we've seen that with reducing car mortalities. We did that from human behavior, not by building more emergency rooms, but by re-engineering cars and roads and educating people better. And buildings don't burn down anymore, not because of something we changed. We didn't change fire, but we re-engineered materials and buildings so they just don't burst into flames. So this is great. I'm so happy you're pulling us all together. I wanted to talk about, I'm just going to throw out one about influenza and birds as a global phenomena. And you could, picking the polar view is not an accident, because that really, influenza is really all about a circumpolar view, but we'll get into North America. If you go to the next slide there. We all know that really the basic reservoir for influenzas, or type A influenzas, are birds. And we have for years been starting to see that wild birds, of course, carry highly pathogenic, low pathogenic influenzas, and trying to get a handle on that. And some of the early work from 15 years ago said, oh, we can just map out migration pathways. And we have big organizations come out with this kind of thing about, here's the migration of birds, which is fascinating, but it looks like we're all going to die, and it's not really useful at all to accomplish anything. So the next slide. There is certainly more refined. So, you know, from our Western Hemisphere view, there are more refined ways of looking at bird migrations, these mass biological events, and get them down a little more refined. But unfortunately, a lot of times it's somebody just hand draws a line to connect a few dots. It's not really that accurate. It's still too broad. This is still not that useful for predicting a flu spillover event from birds into mammals or into humans or into domestic animals or back or forth. So we've been really trying to tackle this for years, and it's really hard and labor intensive. So next slide. You know, we can get out in the field. This is sampling birds for influenza one by one. Next slide. You can gather up teams of people and go and do environmental sampling, not a bad approach to collecting influenzas. And if you have good biologists with you, you can identify the species of birds before they fly off, and then you collect their fecal samples. Of course, influenza, like COVID-19 and bats, or COVID and bats, the original coronaviruses, a lot of the influenzas in birds are gastrointestinal, and they're shedding their feces. Then some forms, of course, become respiratory, and certainly in people, it's a respiratory pathogen. Next slide. Telemetry's really helped us a lot. You can see that swan in the middle has a little antenna coming up between its shoulder blades, its wing blades, and you can track. And next slide. And of course, then we start to get better, you know, more accurate locations on them and timing, so you can follow these birds around. This one's from Mongolia into North Korea, which of course we could not be on the ground to see, but we can see it from satellite tracking. But it's also, once again, expensive, and maybe we were lucky enough to afford to do 20 birds in a year. And so it's not really giving us the level of data, the big data we need. Next slide. So I just want to kind of close with this fact that we have billions of birds, that's billions of birds being born every year. For the migratory waterfowl component, that's 3 or 4 billion that are hatched every year. They're an immunologically naive population. Flu moves through that population at the kind of around the Arctic Circle during the breeding season. Those birds disperse south into across Europe, but down through North America, Canada, North America, and to South America. It's a massive scale. We're thinking billions of birds. We have to be thinking of billions of kilograms of biomass moving around the planet. I don't know another biological phenomena on land, on terrestrial, you know, part of Earth that would match this. We must be able to sense this remotely from space. We must be able to pick up on changes in the environment when you have millions of birds arriving at a site. Water temperature must change, water pH must change. There must be some ways that we can monitor, because we need to know how this virus is moving, not just spatially, but temporally too. So is it this week? Is it next week? When is the risk of a spillover event going to occur? I think we have to come up with engineering solutions to be able to monitor the planet. Especially we can just start in the US if we wanted to, but to really track this kind of biological phenomena, which includes a vertebrate and a virus and the interaction with the
William. Let me just thank you. Let me just put a pause on you there. Thanks very much indeed. Just want to make sure we get through all of our panelists fairly quickly so that we can have our conversation together. Thanks very much indeed. I think it's across to Robert, isn't it?
Hi, can you hear me?
We can, thank you.
Okay, great. So I'm just going to share one slide just so I have a backdrop to talk to. So hi, I'm Bob Bonneau. I'm from actually the Undersecretary of Defense for Research and Engineering. And I guess one of the things I talked to Ubli about in this session was, assuming you've got some algorithms and some things that you'd like to analyze your data with, where's all that going in terms of putting it together, particularly if you've got a lot of remote sensors and things that you've got to connect? And so one of the things we're spending a lot of time on is automating the process so an analyst doesn't have to be in the middle of trying to figure all the mechanics out of how to integrate the data, but it's all fairly transparent and easy to use on the cloud. And so we've been spending a lot of time integrating a lot of different remote sensing functions together, kind of in these very large cloud environments, highly dynamically. And one of the things we're finding out about it is that to get this to work, you need to be able to have not only something that's checking the data itself and guaranteeing that the data is matching the algorithms properly, but you also have to be able to check the infrastructure and understand that the infrastructure is supporting the kind of assumptions you're trying to make about the data as you sort of integrate both algorithms and information services on the cloud. And so we've been spending a lot of time trying to understand how to standardize this process. And I think we've come up with some very good sort of usable techniques to make guarantees of performance, particularly if you have automated analytics and artificial intelligence type routines running, even sort of standard commercial ones that you can buy from commercial service providers. So I think it's important to have a plan for verification and validation of your results before you jump into the sort of mass scale analytics, particularly if you're going to try to predict some things that are life critical, like is your pandemic spreading, and how are you going to address that and trust it, and trust the results as you sort of derive them from your automated infrastructure. So this is a big problem, and it's certainly more than I can describe in detail in a few minutes, but I think this is kind of thematically what I'm trying to convey in a nutshell. So hopefully we can discuss it more in the group, and thanks a lot.
Thanks, Bob. Much appreciated. Pei, a couple of minutes on who you are and where you're coming from.
Sure.
I think we are going to put some slides up for you. There you go.
Thank you. So I'm coming from Michigan, but I'm coming from the sensor network world, where we're actually trying to build sensors so we can actually sense these things. Next, please. So my work has actually focused on animals because they're cute and furry, not because I actually study them. But I actually study sensors, and we know that there's a lot of reason to study them, the COVID that impact us quite a bit, but it's not just that direct impact. In 2019, the African swine flu caused the death of a quarter of all the pigs in the world. And people starve farmers starve when they lose all their pigs. So it impacts us in so many different ways as well. So my focus actually been trying to actually bridge the gap between what biologists need, which is data, and what some of the tools that the computer folks have came up with. And there's a, from the panel, from the discussion today, there really is almost vocabulary difference as well. The biologists are looking at data, and a lot of data means they go out to the field and catch a bird, maybe two for the whole day, and they have 2 data points, and 100 birds will be a lot of data. Sorry to disappoint. The data scientists, on the other hand, have their deep learning models where 1 million data point may be a little low, right? So how do you bridge a gap? How do you actually capture these data? So my work have been trying to figure out sensing techniques that leverage existing structure vibrations to create maintainable and retrofittable sensors so we can capture data on either wild animals or domesticated animals. And then the learning side focused on how do you learn from these small physically collected data and offset it with a bunch of different models. Next slide, please. And so a part of that, looking forward, I think what's really missing is actually bridging that gap. How do we actually have sensors that doesn't make the world look like this, where you put the sensors on everything and it's impossible to deploy and impossible to maintain? I work with biologists who go out and tackle a zebra per day, and that's really a lot of work. I like to sit in the office and just watch nature documentaries. Right? I want the data streaming to me. I don't want to go out. So how do we actually make this sensor network, that sensor system that actually works, that can collect a lot of data? And also, that a lot of data means very little data to the computer folks, to the machine learning folks. So how do we actually learn on this really sparse, very noisy, and that changes with the environment, all these smaller type of data? And this wide scale sensing, I will argue, doesn't just mean in the US. We work on pigs. So in the US, there's a lot of industrial farming. I think 99% pigs are in industry farming. I also work with people in Thailand. Those farmers, they have 2 or 3 pigs per farmer. They sleep with their pigs. And there's also these rural-urban animal divides. It's how do you actually form, and then how do you actually form these sensors so they can actually monitor across this wide range and make it maintainable for a long term? And of course, it's not just engineers alone can do this, because I don't understand a thing about animals. And how do you form these partnerships between the biologists and the folks that willing to build tools?
Okay, thank you very much indeed. Tierra, nice and briefly again. I can't see Tierra. Ah, I can hear your voice. Lovely. Thank you. A couple of minutes.
Hi, I'm Tierra Smiley Evans. I'm from the University of California, Davis, and I work at monitoring at the human-wildlife interface. So I'm more on the side of practically how do you get your hands on these wild animals and how do we collect samples from them. And where I would really love research to be focused in the next coming decade here is improving our understanding of where these high-risk interfaces are. I think we heard a lot about that this morning, that we have kind of a crude understanding of where the hotspots are around the world, but we don't have a lot of resolution to that. We know pieces of the puzzle. So we know that pathogens that have high viral host plasticity, so pathogens that can move from multiple animal species, are more likely to spill over into people, and if they do, are more likely to be transmitted to human to human. So they have higher pandemic potential. And we know that interfaces that have these pathogens and also have diverse species mixing, as well as people engaging in activities that allow for opportunities for transmission, are places that we need to monitor more. But what's really needed in the next generation of research is more landscape level investigations of the underlying mechanisms that's driving increased viral host plasticity, so that we can understand how we're altering our environments, how we're altering our ecosystems to create these sort of perfect storm scenarios where these pathogens can evolve and spill over into people. And once we have a better understanding of that, we can know where we need to focus our energy for monitoring. Next slide, please. So regardless of where those locations end up being, we know that it's going to be far beyond whatever scale we as a research community could ever tackle. So where I'd like to see things really going in the future is more towards community-led monitoring. How can the communities that live in these important dangerous interfaces monitor the human behaviors and the wildlife behaviors in their own communities? So that's going to require a lot of advances in field-forward data collection as well as sample collection. So for example, how can we harness some of the smartphone data technologies that exist already to empower citizen scientists to collect their own data? This photo here is an example of us working with the Myanmar logging community, the elephant loggers, to actually go into these pristine forests throughout the country to help collect data for us. So we're working with those communities to understand those interfaces. And eventually, how can we move more towards handing over biological monitoring of wildlife entirely to communities? So that's going to require a lot of very basic advancements, like how do we eliminate cold chain requirements entirely? How do we move more towards microsampling mechanisms so we can use just a drop of blood or just a drop of saliva to get the kind of information that we need? And eventually, how can we even bypass the laboratory altogether? How can we work towards more next generation point of care testing for wildlife pathogens? Next slide, please. And lastly, as I'm also a wildlife veterinarian, I'd say that we spend a lot of time sampling quite well at some of these really important interfaces, but at the wrong timing. So I'd like to see there be a lot more focus on better understanding viral shedding patterns in wildlife. And that requires going back to the same population over and over again to understand trends. And when you're working with species such as non-human primates that are really intelligent, that's going to require completely removing humans from the scenario. So looking either non-invasively or through some of these really exciting remote deployed sampling mechanisms. Our group has been working quite extensively with how do you collect non-invasive saliva samples from wildlife and looking for RNA pathogens. But you know, there's a lot more research that can be done there. How could we potentially look for antibodies or other types of pathogens as well? And how can we utilize some of these biosensors that we've learned about today in wildlife that are being developed for human medicine? And eventually, as the platforms and the labs move to smaller and smaller sample sizes, how can we use things like mosquitoes to do our sampling for us? And lastly, I just want to say that we've heard a lot about molecular diagnostics today, but I think that serological methods are going to be really critical going forward to understand both the human and the wildlife behaviors in these really important interfaces. So I want to make sure that investments in those sorts of platforms are going forward as well.
Tierra, thank you very much indeed. Much appreciated. We'll move on swiftly because I want to get to our conversation amongst you all. But first of all, let's hear from our last two panelists here. Juan Carlos, I think you're up next. I think you're going to use your own slides. Is that correct? Yes. So
yeah,
a couple of minutes. Thank you.
Yes. Hi, and thank you for the invitation. I'm a biochemical engineer and have dedicated quite a lot of my professional life across multiple industries and institutions to the Amazon. And you might have heard that the Amazon tipping point is very near indeed, meaning that there is a high probability, not a low probability, a very high probability of the tropical forest equilibrium being changed to a degraded savanna equilibrium. This will have, of course, catastrophic impacts in multiple dimensions of climate and so on and so forth. But this becomes very relevant to our conversation if, like Peter said in his keynote in the beginning, that the Amazon is home to the largest pool of undiscovered zoonotic viruses, particularly the ones in bats and in rodents, but particularly in bats. Now, the Amazon basin is a beautiful place, very large indeed, very complex. It's amphibious. Half of the time it's completely submerged in water, and it's highly, highly inaccessible. So much so that scientists and ecologists walking in the edges of the Amazon are able to discover one new species to the world every 3 days. But that's probably only at max 1% of total life that exists in the Amazon basin. And by life, I mean all forms of life, including, of course, the viruses that we're after. Which is why we now, for about 2 years or so, we've been designing and prototyping and testing a swarm of autonomous sensing systems to discover potential zoonosis. And this little red circle that I mentioned to you here just allows me to tell you the story that there are about 3,500 types of bromelias species in the Amazon. Bromelias are very high up. They can store anywhere between 2 liters of water to 10 liters of water. They are the drinking grounds of monkeys and bats and all sorts of other species. They also have, some species have nectar that attract particular species of bats. And it is in this very targeted place that is very extensive in the Amazon, where we are hunting for biosignatures first. And José mentioned the key word for us, which is metagenomics, really understanding the signatures of where the different virus families may sit in hosts. And we are currently, so we've done quite a bit of design work, quite a lot of prototyping, but we're very in the early stages of developing a cross-disciplinary, cross-sectoral science and engineering blueprint and roadmap to actually develop this at scale. And the reason why is we are after an Amazon-wide early warning system. We believe it is not a question of if, but actually when, where, and what will emerge. And so I thank you for that and look forward to the conversation.
Juan, thank you very much indeed. Nicely done with the timing. So finally, our last panelist before we get into the big conversation, Wayne. Wayne, I think we're going to share your slides for you, aren't we?
Yeah, so I'd like to thank the organizers for putting this workshop together. It's really been wonderful and I'm learning lots of stuff. Next slide, please. So what I wanted to talk today, very briefly, just present a little bit about my thoughts on using animal movement trajectories and the segmentation of these trajectories as a way of perhaps identifying stressed or sick animals or assessing how animal behavior has changed in response to anthropogenic factors. So I've been thinking quite a while for the last 15 years about animal movement. And I have come up with what I call a hierarchical segmentation paradigm, which I think is useful for having a look at how behaviors change at different scales. And I think scale is a very important component of trying to understand the response of animals, and also as a diagnostic tool on perhaps the internal state of animals and whether they're stressed or sick. Now, at the center of this segmentation is what I would call the daily activity routine, which is the green activity in the middle there. It keys in, it's a diel time scale, and there are different types of daily activity routines, and they may be played out in different ways at different seasons, and also when the animal is in various states. But how do we understand the daily activity routine of an animal? So if we're looking at relocation data, Susan in her talk showed us the movements of various cats over the landscape as a bunch of points. And these points are made at a particular frequency. And in order to be able to understand some of the fine scale stuff, it would be technology has been improving, and we are able to monitor the relocation of animals at higher and higher frequencies. It used to be that an hourly basis was fairly standard. Now we're down to minutes and even seconds. Now, at the bottom end of this hierarchical segmentation, or what I call the fundamental movement elements, Those are those blue circles on the left. And there may be a number of different types. Classically in the horse, you get walking, trotting, and different movement patterns depending on whether 1, 2, 3, or all 4 legs are off the ground at once. But most animals are not that easy to pass out into fundamental movement patterns. And that's more a problem of biomechanics to understand that. At the next level up, if you say, looking at a scale of tens of seconds, a minute or so, you have a sequence of fundamental movement elements that I call a meta sequence of fundamental movement elements, or a metafume. And you can get the statistics of what the metafume are in terms of the number of steps taken, the size of steps taken, the directions of heading from one step size to the next. And the size of a metafume depends on the frequency at which you collect your data. So if you're collecting the data once a minute, then your metafumes would have to be on the order of several minutes. So it's better to have higher frequency data, and that's what we're going to try and head for in the future. Now, these metafumes may be put together in ways that you can interpret as canonical activity modes. A canonical activity mode, a classical canonical activity mode, may be an animal heading to a particular site, heading to water, heading home, or whatever. Other canonical activity modes may relate to feeding strategies, searching strategies, or various other sorts of things that you can put together as one activity that the animal is focusing on for a period of time, say on the order of some minutes or even some hours. At the other side of the daily activity routine is if you put together a number of daily activity routines, you might get a life history movement phase. A good example of a life history movement phase is an animal undergoing migration for several weeks or months, or an animal that is in a nomadic phase, or an animal that is in some other life history phase.
Wayne, just another 30 seconds, please, then we'll move you all onto a big discussion.
Next. So my next slide shows that there are a number of methods that have been developed: step selection functions, home range mapping, resource habitat selection, hidden Markov methods, and breakpoint methods for analyzing these pathways. And although we have a lot of mathematical and statistical methods, the most important thing at this time is to get higher quality, higher frequency data. Thank you.
Wayne, thank you very much indeed. And thank you all of our panelists. So as an audience, we now have a good understanding of the perspective that everybody's coming from. And I'm going to hand across to Christine now to sort of start the conversation off amongst the panel, please.
Yeah, thank you all so much. I think this is really fascinating panel discussion already, building on some of the things that we heard this morning. And I guess just building on the talk that we heard this morning from Joe Wang around the nanoscale sort of tattoo sensors that he talked about, that some of us were just starting to like, our mouths were watering over that idea. I guess broadly for all the panelists in this panel, what are the needs? What is the sort of the next generation in animal tracking? What are the biological needs, and what types of sensors or trackers do you think would work? And I guess I'd love to start over to Billy, just to hear your thoughts, because you started very much on the avian migration, which I think for flu has some really obvious inferences around that would be a priority.
Okay, well, I mean, certainly, as we know with birds, I mean, we're limited by weight. So any of the traditional tracking devices, because every gram you add to a bird that has to fly at 25,000 feet and maintain its caloric, balance and get to where it's going is going to be compromised. I think that, the smaller the sensor, the better. But, I think the other thing to consider, and what, came up with Juan Carlos, is about some environmental sensors that give us the information about the bird. So do we have auditory monitoring stations that pick up on vocalizations of animals or birds and can remotely identify that. You know, satellite imagery is the resolution's much better. One of the questions came up on the other site about, you know, using radar data and moving that and really building in some, you know, machine learning, artificial intelligence to make that data more useful. You know, we can get a Google Earth image every day, you know, and see exactly where certain groups of animals are, and they can get pretty good resolution. So I'm wondering how much we can actually move away from tagging the individual animal to monitoring the environment to pick up on animals arriving, coming and going.
Excellent. That's really helpful. Yeah, it's being put in the chat and coming up a lot in Kai's terms, sort of what is your magical sensor wish list? Maybe over to Wayne next for your thoughts on environmental versus individual animal monitoring.
Right. So I think there's three kinds of data. There's first the location of the animal, GPS telemetry, or reverse radar methods, and being able to place animals at precise points at high frequencies. And there can be a lot of improvement in technologies for doing that, and we're seeing that accelerating every year. Then there's measurement of the external state of the animal and measurement of the internal state. So the external state is characterizing the local environment at an appropriate scale of resolution, and we need to be able to do this at finer and finer scales, which means huge increases in the amount of environmental data that we have, and the sort of physical and spatial factors, even three-dimensional structures, using things like LiDAR that we can use to characterize the landscape. Whereas with internal states, we've seen some discussion about monitoring the state of humans. And somebody asked a question about how can we do this with animals? I think a lot of us here want to be able to do that with animals, their physiology. Temperature is an easy thing, but online real-time stress hormone levels, these sorts of things, that's where we hopefully can go in the future.
That's great, Wayne. I think others on the panel, especially Pei and maybe Bob, on what would be our wish list for this and how can we get there?
I can give it a shot. So we started off working on getting location data many years ago on the ZebraNet project, where we were using GPS to get the zebra migration patterns. We as computer folks weren't able to do that because all we see is a bunch of dots on the screen. We don't really know what that data represent. The biologists that were working with us was really good at looking at that data and figuring out exactly what the meaning of those data is, what the behavior pattern of that zebra is. And I think that is one thing that kind of inspired us to do the work currently, because that data has a lot of hidden information where the biologists have these internal models that outside people doesn't know, and they were able to apply and provide the understanding. Realizing that, what we're currently working on is perhaps this sensor that we are measuring the structural vibration of a building, namely the farm that the pigs are housed in. So when a pig moves, they create tiny earthquakes in that building, and the vibration sensors capture that vibration. From that, we can deduce pig behavior, like how likely they are to crush the little pig, how unlikely are they sick, how likely are the pig's activity level indicating some other issues. Give you an idea how sensitive that sensor is. When a pig is sitting on the ground, the sensor is 2 meters away. We can sense its heartbeat, right? But those data are just data, just vibration data. It has to include all these other, the biologists' models, the veterinarians' models, and the structural building vibration models in order to get the animal behaviors. Right? So we have teams, there's people that work on veterinary people on the team. There's structural engineers on the team. There's an earthquake engineer on the team. And of course, electric people. So these kind of, I think these magical sensors, yeah, we have our wish list, But I think with my wish list may be different than the biologist's wish list, because biologists may not know what sensors are available. I may not know what the biologists need or biologist's internal model has that can interpret what data I have. Right. So yeah, there's a lot that we can do. I think that's
why we're here.
One of the questions that I wanted to raise with the panel, and maybe we'll start with you, Bob, is that, as you can see, a number of the panelists have expressed desire to have information about animals at pretty fine scales, but as has been disclosed, instrumenting the Earth is quite challenging. And so, based on your perspective, I'd like for you to offer some potential solutions as to how engineering and technology can help with this spatial scaling issue that we have.
That's a great question. So I think what's going on today is that there is a lot of commercial services that are becoming available, whether it's at the embedded device sensor level or it's at the sort of large scale data level. And so part of the challenge is to select the services that maximize the thing you want to know. And so what we're doing these days to sort of aggregate things that are globally important is, first of all, you've got to have a sort of resource pool of information services that you can, draw from. And once you have that, rather than sort of pre-specifying which of those services actually are, you're going to choose a priori, you essentially both choose the service and the data from it dynamically until your hypothesis gets validated in real time. So you're not just sort of pre-specifying your data, and you're not just pre-specifying your service, but you're in effect pre-specifying the way the architecture gives you a result. And if you kind of use that approach, you can start to weed out very quickly the things that aren't particularly useful to get to the hypothesis you need. And if you're paying a lot of cash for this, you're also weeding out the expensive services that really don't provide you a lot of value added. So, so this idea of learning both on what services you use and also, what data sort of incrementally they provide you to sort of back up your hypothesis is kind of critical. And that's what we found is the most efficient way to scale these processes, because otherwise, it's a human in the loop trying to figure all this out in real time, and that's very inefficient.
Christine, maybe I can compliment?
Yes, please.
Yeah, compliment both Bob and the other panelists. I think that the only approach is one of adopting multi-scale approach to sensing and then predicting. A particular example in the Amazon basin is that this savannization event is probably already started. And so we are using passive microwave sensing that actually detects water content in the trees that tells me the change in the species composition of trees in the Amazon, which therefore is an indicator of stressed animals in and around those trees and those regions in the Amazon. Then we therefore then have a view of hotspot of where then to launch the next layer of sensing. And I've commented on one particular point, which is the drinking spots of bats and monkeys. Mm. And beyond that, and going to the wish list and the type of sensors that actually we're deploying, it's meta X, where X could be volatile organic compounds, because everything smells, has a smell footprint, if you will. Acoustically, everything has a signal as well, has a very specific, Jose would call it a signal footprint. In addition, of course, metagenomics and meta-X is our approach to get to the next level. And in the end, we need to sample, and sampling by people is great. It's important, but it will never scale in territories like tropical forests around the world, and just the Amazon as an example, which is why the use of autonomous system is so important for sampling.
Mm-hmm.
And
Yep.
for sampling, of course, you need a strategy, because you can't sample the entire Amazon basin. You have to sample, you have to understand the points, the hotspots, and the frequency of
Yep.
where you want to sample.
Yep. And the research question. And I think you brought up a great segue to my next question. And if it's okay, Tierra, I'm going to put you on the spot. I think the indicator species question that we posed to Sue is really important. I mean, as Juan is saying, we cannot be everywhere all the time. We do need some indicators that can help shed some light on these fundamental processes. And you talked about host plasticity, which we think is a pretty important early warning signal for pandemics. And I guess I'm gonna, if it's okay, toss you the question of what are the big indicator species for virus host plasticity, and building on some of the insight that Wayne shared, which are, you know, we've got spillover happening, and some of these animals, you know, even before it gets to humans, they're getting quite sick. And they might be an early warning symptom that they're sharing of viruses, you know, out there in the wild before spillover. So what are your thoughts as to the key species if we had limited funds and limited logistics to do everything?
Yeah, well, I work a lot with non-human primates, so, you know, because they're so genetically similar to us, I think they're good indicators of what could be. If something spills over into a primate, it's likely that it can also spill over into a human. So I think if we have limited resources and we really need to only pick, you know, one or a handful of species to focus on, looking at primates that are in close proximity to humans are a good place to start. We talked a little bit in our panel discussion, in our breakout session earlier, about how mosquito-borne pathogens are really important, because if there's the opportunities for mixing of multiple species and crossing barriers via vectors, that you don't necessarily have to have wildlife coming into contact with each other. So I would say that's the first place to start. And just to jump back to the wish list, since I don't want to lose my wish, I've been thinking all day about how you could possibly put those little tattoos onto a gorilla, but I think they would spend all day trying to pick those little tattoos off because they love to groom each other. So if there's any way that we can move some of these sensors towards things that can be swallowed, things that can be, you know, even if it's just the short period of transit time that they're in contact with the host, but how can we move sensors into the realm of small things that aren't on a choking hazard, but that can be swallowed and collect information as they move through a primate or another species.
Mm-hmm. That's great. And I'm going to add to that same idea, because we do really well if we get our hands on the animals, dropping these little tiny transmitter beads inside them. If they can actually talk to satellites, that would be brilliant.
Could I pose a combo wish?
Yeah.
Please do.
Maybe
Now's the time.
Do we have time?
Yeah, now's the time. Yeah.
You know, could we take let's kind of be bold and take a landscape like Yellowstone National Park, or the whole eastern seaboard of the US. In Yellowstone, we have elk and bison and wolves are already telemetered. They have attachments. You know, should we take the whole park and put out ground vibrational sensors, match that up with overhead satellite telemetry, pull all that data together, learn, you know, you could probably feel a wolf pack running, and you could determine if they're running for a kill or they're running or walking along to move. You certainly could pick up vibrations from bison and elk, and they migrate seasonally, and there's altitudinal migration up and down. And and Defense Department, we know they have ground sensing kind of data technology, or the eastern seaboard, monitor the flyway, and you have environmental sensors, and there's air sensors picking up viruses. You once again auditory signals as birds arrive, and just do something. You know, go to NSF and come up with a big bold idea to roll out one of these integrated approaches, model system.
I think you raised a really important question, which is kind of the big question across this entire workshop that we are all struggling with. And I've noticed it, especially with our biologists, et cetera, is that, to quote Juan Carlos, you've developed these meta-X strategies, right, to infer things about the populations you care about. And one thing that's missing right now is an ability for us to share those learned techniques across a lot of different disciplines, even to the point of having, if you might say, a job or message board that says, I need to be able to do X. And then we need another way to get engineers who might be working on very exciting problems, but may not be aware of the fact that they have tools and techniques with the proper domain experts can be brought to bear on this. And this crossing of disciplines so that we can help each other. This is the big question of the workshop, I think. And given that so many of you have some experience in this already, it would be great to hear your advice as to how we might do this.
So I'd like to make one important point, and that is what we're really looking at is a boundary problem. Disease is a natural part of an ecological system, and you want animals to have the disease processes that go through them. They're important for evolution and all these other things. So given the limitations in resources, what we really want to look at is at the interface. We want to be able to identify the boundaries better, compare what's happening on the boundaries to what's happening on either side of those boundaries, and really find a better way to identify boundaries and to focus on them.
Beautifully said, I think. Have we got any more time? Have we used up all of our time?
You have a couple of minutes if you have one closing killer question.
Or any panelists that want to top up. I think we've really brought to bear some important issues around the transdisciplinary needs. And I think getting professions together to address these issues. From the biologist perspective, we often feel like the engineers are volunteering their time outside of their normal day to help us with these challenges and tracking. And I think it's really good to see some of the advances.
I want to disagree with you on that. A lot of engineers are working with biologists, not because we're volunteer, but because we are actually publishing new research as well. Right? And that's really where the opportunity lies for these cross-boundary things, especially when biologists may not be able to find the sensor that fit their need, and us can find a new application with new twist to apply the sensing technique that we have.
Yep,
and that's really a great combination.
That's right.
I can also say that being trained as an applied mathematician, I really enjoy working in the biological world. So it's not about volunteering, it's about enjoying the questions and enriching our lives.
So I think if you think about the biologists as analysts, the analysts need to trust what the engineers are providing them. And the probability that they're going to trust that needs to be quantified so that they understand how much they can trust that data to give them the result they're after. And I think one of the things we spend a lot of time doing is trying to give analysts confidence that the automated results we're providing them actually are trustworthy, so they can actually, publish them in this case. So, so the question is, how do you reliably do that repeatably? And I think there are good lessons from a lot of the verification and risk analysis type statistical things we do that sort of can inform that process. So.
But I think as engineers, we also need to be taught how to ask the right questions, because sometimes what we think is interesting to analyze is not actually something that's of utility to our biologist colleagues. So this really is a two-way conversation, both about the trust, but also the understanding. So we have to make sure we don't have the hubris to say, well, obviously, this is the data analytics that you want, which is equal sign to this is what's easy for me to compute, versus, again, what's the important questions to be asked.
But for anybody who works with data, I don't think you can really understand what the data really means if you haven't seen how it's collected. And sometimes you get quite shocked about how dirty the data really is. You have a kind of an idealized view of the data if you don't really see the way it comes in. And that's not to denigrate the people who are collecting the data, but it's just such an enormously difficult problem that to appreciate the complexities and difficulties of collecting data, you have to see how it's done.
And on that note, could I put a close to this conversation with a round of applause for everybody's contribution. It's been a fabulous, fascinating conversation.